Everything produced by mankind has a lifespan, but when that span is complete, it's often not the end, but just the beginning of a whole new existence. From destruction to renovation to transformation, this cycle of life, death, and rebirth happens in amazing places called boneyards. Virtual cities on the sea, offshore oil and gas platforms, and the rigs that drill them are among the largest man-made objects on Earth. Like icebergs, only a small portion appear above the waterline. Designed and built to ride out storms and earthquakes, they can be maintained to last for over 50 years. Most will outlast the deposits of oil and gas they've drilled and sourced. A boneyard of metal giants, waiting for new technology and new deposits to bring them back to life. Some will be cut down and pulled from their moorings, brought ashore to coastal boneyards, where they'll wait to be refurbished and sold to new operators, parted out and reused in new rigs, or cut up for scrap. Today, many are finding new roles. Some are converted into artificial reefs, and in the Gulf of Mexico, they're being reborn as producers of energy from a source that's abundant and endlessly renewable. Thousands of giant offshore drilling rigs and oil and gas production facilities in the Gulf of Mexico play a crucial role in supplying the energy that keeps America running. But when the oil or natural gas below has been tapped out, or the platform has reached the end of its useful life, its wells must be plugged and the platform removed. And that's why the coastline of the Gulf is dotted with vast boneyards crowded with these hulking structures, like this one at Bisso Marine in Amelia, Louisiana. The upper deck's living quarters, helicopter pads, and towering support structures called jackets butt up against each other, awaiting their fate. These structures represent millions of dollars in materials, most of which is steel, and the high price of steel dictates how much of that investment can be recouped. Many will be cut up and sold to scrap brokers in other boneyards. Some will be sold to other operators and returned to work at sea again. Some will be cannibalized for their parts, and still others will be converted to a growing number of alternative uses, a testament to their robust, adaptable designs. When these remarkable machines are towed ashore, they're coming home to the very same places where they were built. It's only fitting because the offshore industry was virtually invented here on the Gulf Coast, with its industrious, creative Cajun community.
There's a tremendous amount of native ingenuity within our facilities. There are no blueprints behind on how to do it. The Cajun ingenuity in the facilities here, we present the problems to our challenges to our people. In turn, they look at what we have, and they end up with a finished product that makes us all very proud for what we do.
In the early 1900s, America had yet to complete the transition to the horseless carriage. Yet wildcatters were already exploring methods of drilling for oil offshore. In the 1940s, drillers from Texas and Oklahoma flocked to oil-rich Louisiana, venturing their drilling rigs into the marshes and shallower waters of the Gulf of Mexico. But they soon realized that drilling offshore was a whole new ballgame.
When you're drilling offshore versus inshore, it just complicates everything because of, one, transportation and just logistics. Inshore, you may be spread out over several acres. Offshore, you're confined to that one structure. So whatever levels on that structure, you can put everything, which is storage, all the equipment, everything you need to drill that well has to be right there or readily accessible through boats.
The early rigs were taking land drilling rigs that you would have in Oklahoma or Texas and place them on small cargo barges, move them out to a location, and you'd place ballast water in the lower hull and have it submerged to the bottom and leveled, and drill wells that way.
Using barges, drillers were limited to shallow depths under 20 feet. After World War II, however, drillers redoubled their efforts buying cheap ex-military equipment from war surplus. One of the many support vessels obtained from surplus boneyards was the Navy's LST, or Landing Ship Tank. The vessel made an ideal support boat for the very first tender platform drilling rig in the Gulf, off Morgan City, Louisiana.
It was a platform which handled the actual hoisting system, and the support equipment was on a LST vessel. They joined the two, and they had living quarters, areas for the equipment, and finally the drilling rig was on a platform.
Although much has changed over the past 50 years, tens of thousands of platforms for both drilling and production facilities have been built using the same basic design: a topsides or deck and a support structure called the jacket.
What we call a jacket is actually a template that sits on the bottom of the Gulf of Mexico. After the jacket is set, piling are driven into the legs of the jacket and stick out about 4 or 5 foot out of the jacket. Then the deck section is set and tied into the pile sections. It can be either a production deck or a drilling deck. Production deck normally has a lot of production equipment. Once the oil or gas comes into it, it can facilitate it and get to land bases or whatever the oil company tends to want to do with it.
The fixed offshore platforms built at Gulf Island Fabrications in Houma, Louisiana, work in up to 900 feet of ocean.
If you were to take a ride offshore, you'd only see about 10% of what we actually fabricate here. The part you see is the big decks, the jackets. The hard work that we put into the facilities, in some respect, is underwater. It's deep six. You can see the size of the platform behind me. And again, less than 10% of that will be above water.
The jacket is made of giant steel pipe sections referred to as tubular members.
We typically take a flat piece of steel. Our mills roll them, we weld them, we then join those sections together, and you end up with a 300 to 400 foot can or a jacket leg.
Much of the cutting and welding at Gulf Island is automated. As the braces and legs are welded together, the jacket begins to take its final form. The U.S. Minerals Management Service requires each component of the assembly to be ID'd with a tracking number.
If they get a failure offshore, they have to be able to go back and check if it was a materials aspect, if it was a welding aspect, or what. God forbid any kind of catastrophe that would happen. But they can actually go back and track each weld and each piece of pipe that we use.
It's one big machine here. What you see here is it went through the process of our rolling mills to our cutting tables, to our brace cutting facilities, to our welding facilities, into the completed structure you see behind me.
Although engineered to withstand incredible stresses at sea, the jacket is vulnerable to stress when it is loaded onto the barge that will transport it offshore. The giants are moved by Mammoet transporters, remote-controlled flatbed vehicles with so many tandem axles, they look like centipedes on roller skates.
The capability of these transporters is 200-ton capacity per transporter. We currently own 6 transporters, which equates to 1,200 tons of lifting capacity.
To prevent stress on the jacket, the loadout must proceed slowly and methodically. Even if nothing goes wrong, 8 to 15 hours for the job is typical. The jacket is pulled onto a ballasted barge with hydraulic jacks called strand jacks. So great is the stress that the steel cable in the operation will never be used again. It goes to the boneyard to be cut up, melted down, and recycled. Finally, the jacket is secured on the barge and bound for its new home. Years from now, after the jacket has outlived its time in the Gulf, it may come back to this yard in Houma, Louisiana, or another nearby. What happens to it next depends on its structural condition and usefulness.
We do a lot of refurbishment work. They might bring in a jacket that was set in 200 foot of water. They might cut some out, make it for 140 foot of water, or different water depths. They can also add to it, make it for deeper water.
But many of the platforms in the boneyard won't be leaving it again until they've been cut up in pieces. Welders dice up the structures, cutting the metal into sections. The sections are craned over to another part of the yard where they're cut into smaller pieces. Then loaded onto trucks with a magnet grapple. The pieces may be hauled to Southern Scrap in New Orleans, further processed and barged up the Mississippi. Scrap brokers sell it to steel mills, where it is melted down and made into new steel.
The mills will actually cast the steel again to be reprocessed back into the next project we have.
2 offshore facilities that escape the cutting torch sit just a few miles upriver from the Gulf at Morgan City, Louisiana. One is a small production platform. The other is an historic drilling rig known as the Mr. Charlie. Named for one of its investors, it was the world's first submersible drilling rig. The Mr. Charlie drilled its first well in 1954, the first of more than 200 in its remarkable 32-year career.
When the Mr. Charlie went out, it was the first movable rig, so it was a rig that you could use over and over again. So it just revolutionized the whole industry because you weren't spending $250,000 building a platform for a one-time use.
The Mr. Charlie was the brainchild of Alden J. Doc Laborde, a former naval architect.
That there would be a better way to do this was obvious to anyone out there, so there was no great stroke of genius. But I knew a little about the water and the ocean and waves and things that I don't think these Oklahoma drillers had much idea about.
In spite of all the skeptics who said it would never work, the rig made a huge strike for Shell Oil on its first drilling job. Built for $2 million and backed by the Murphy Oil Company, the Mr. Charlie had accommodations for a crew of 58 and everything else necessary for drilling. The barge was sunk on site, using the weight of the water to help anchor it in place.
It was the first step into the deeper water, and it was excellent. You had a lower and upper hull and extension stability legs, and it had what's called a keyway, where you would drill not cantilevered off the side of the vessel, but within the vessel.
But by 1986, the Mr. Charlie was outdated. Drillers were using more advanced and efficient technology and moving into greater depths. In the early 90s, Doc Laborde's company, Ocean Drilling and Exploration, ODECO, decided to retire the rig and cut it up for scrap.
I just couldn't see any reason to cut up that piece of history.
Through Virgil Allen's efforts, money was raised to buy the Mr. Charlie and preserve it for a new life. Today, companies bring their prospective offshore hires to work, eat, and sleep on board for a 14-day trial. It's a 24/7, hands-on experience on a working rig. Some may decide the life is not what they expected and get off. For others, the Mr. Charlie opens up a whole new world. But even if it had been scrapped, in the continuing cycle of offshore life, the Mr. Charlie's steel may well have ended up in even newer and greater rigs and platforms. Every offshore oil and gas structure is surrounded by potential dangers. Storms, rogue waves, payload stress, accidental collisions from passing ships, and corrosion are just a few of the forces that can mean a premature trip to the boneyard. Following criteria established by the Minerals Management Service and the American Petroleum Institute, the design of each platform must allow for the stresses and hazards particular to its geographic location. Platform Gale, for example, is one of more than 33 structures off the coast of California where critical design includes the ability to survive earthquakes.
Platform Gale is a drilling and production platform. We're about 10 miles from the coast of California. We have survived earthquakes on the platform without any major problems. They're fairly rigid. It's like being on the end of a whip when you've got this structure that's 750 foot tall, and it wants to sway quite violently at the surface.
Owned by the independent oil company Veneco, Platform Gale is 900 feet tall, most of which is underwater. The jacket is anchored in place by steel pilings hammered several hundred feet into the seafloor. Radar reduces the risk of being hit by passing vessels. The platform's radar signature not only identifies it, but makes it appear considerably larger than its actual size. Erected in 1987, Gale has endured many natural disasters. But despite its robust design, Platform Gale can still succumb to the same threat that has ended the careers of more offshore structures than any other: an unsatisfactory profit margin. In 1999, when profits became insufficient, Chevron, the company that built Platform Gale, sold it to Veneco.
Veneco is an independent oil company, and we specialize in oil recovery from older oil-producing facilities and leases. We feel that with our lower overhead that we can accomplish a profitable business by producing these older platforms and older facilities. The oil prices stay high enough, why this would be profitable for probably another 20 years.
The higher the price of oil, the longer companies can tend to stretch out the life of a platform. When oil was $20 a barrel, $15 a barrel, the companies here were talking about pretty quick turnaround time for decommissioning, and now you rarely hear it.
The platform currently produces over 11,000 barrels of oil a day from more than 24 wells, which vary in depth from 6,000 to 16,000 feet.
The Monterey, the Sespe, the Upper Topanga, the Lower Topanga, those are names of the different producing geologic zones.
Gale generates its own electrical power from turbine generators that run on natural gas, produced from its own wells called sour gas. Because the gas from these wells contains a poisonous compound called hydrogen sulfide, this compound is removed from the gas, producing a waste product called sulfur cake.
That sulfur is actually a product that we give away to a local company, and it becomes fertilizer.
Platform Gale, like most platforms, is a city unto itself.
We operate virtually self-contained here. We make our own water from the ocean, desalination units. We generate our own power. We have our own sewage system. And the only thing that limits our stay is food deliveries.
Barring unforeseen developments, Platform Gale will be 40 years old by the time it has reached the end of its useful life and is scheduled to be removed to shore. Regardless of the reasons why, the process of removing these structures is a highly specialized job, utilizing many of the skills and equipment common to marine salvage, including divers, heavy lift vessels, welders, and munitions experts. Based in Houston, Texas, Bisso Marine is one of the busiest salvage and heavy lift companies in the Gulf.
Bisso Marine is a unique contractor in that we do full-service offshore and inshore marine salvage, wreck removal. We do heavy lifts. We're involved in the installations of structures, servicing structures as they need things over the years. And sometimes, unfortunately, we're more or less like the undertaker, and we have to go in there after a casualty and take the components out, deliver them back to the customer if they choose to scrap them or reuse them.
Working with Rowan Barge 415, the crane on Bisso's derrick barge, Boaz, provides the muscle for a wide variety of offshore jobs. The shackles on this 4.5-inch chain weigh 700 pounds apiece, with a working capacity of 500 tons. This monster is controlled from a bright yellow room on Rowan Barge 415 called the schoolhouse.
In this room, we have the survey people that put us on location and determine we're in the correct spot. We have monitors, and with that, we can watch the wire go down as it's being lowered to the diver, where he can make it up to the chain, all through the controls here on the panel.
With the right machines, lifting a steel giant from the ocean floor is easier than you might think.
Okay, this controls our number 5 winch, and it's as simple as a turn signal on your car. It's a real light, easy pull, and with that, we can get 1,000 tons.
All the underwater work, the cutting, rigging, setting explosives, and other activities are performed by the diver, with support from Barge 415.
We are performing mixed gas dives. We are doing heavy rigging, jetting, burning on this job site, and everything's controlled from right here.
Working at depths of over 250 feet, the divers can only spend about 30 minutes underwater to avoid nitrogen poisoning. After each dive, the diver will spend approximately 90 minutes returning to the surface and 2 hours in the decompression chamber. During each dive, the diver earns his pay doing a difficult job under hazardous conditions.
The equipment that he's working with is 500-ton equipment. The size and the weight of this is astronomical. A shackle, which looks like a U that connects chain to cable, is as tall as a man. It's 6 feet tall. To connect this is very difficult because you've got nothing to stand on, so it's pushing and pulling.
Watching the monitor feed from the ROV, remotely operated vehicle, the topside crew lowers the cables, chain, and gear the diver needs to cut and harness the heavy sections of rig for removal.
We support him as best we can from the surface. We help him out there with the leads for the different tuggers that have to pull on the shackles or the heavy straps. But the man is down there on his own. He's going to do the job.
When working on smaller rigs, the entire structure is sometimes removed in one piece, placed on a barge, and taken ashore. But a large production platform requires a different technique.
Basically the opposite of the installation process. You start at the top, you remove the helideck, then you take the topside facility off, and then you run some type of a cutting tool or explosives down the piling, and you cut the piling, and then you just simply lift the jacket away, leaving piling 15 feet below mudline.
But when powerful hurricanes like Katrina and Rita strike the offshore oil fields, they create a path of destruction that will take years to clear. However, for the men and machines charged with picking up the pieces, there's more than one boneyard. In the Gulf of Mexico, there are thousands of working oil and gas platforms, as well as thousands of idle ones waiting to be removed. In some places, the idle platforms represent a visual history of offshore technology.
The first platforms were creosoted pilings, and most of those are still standing. They were put up in the late 40s and early 50s. And the next technology was the concrete platforms, which were put up in the middle 50s, and then the steel platforms took their place. The steel had many advantages in the fact that they could be recycled.
Working deeper offshore created the demand for different types of drilling and production rigs. Technology advanced. Today, some older rigs, designed to work only in shallow and flat areas of the Gulf, may be idle for months, even years, waiting to be refurbished or scrapped, in the shadow of new generations of stronger, more versatile rigs.
We'll sell a rig whenever we feel like it's reached its full maturity and that it will no longer survive the environmental criteria that we're trying to work in.
In recent years, however, hurricanes have sent more drilling rigs and offshore platforms to the boneyard than obsolescence, oil prices, or any other cause. In 2005, Hurricanes Katrina and Rita impacted thousands of platforms in the Gulf. Over 100 were destroyed, and up to 200 damaged badly enough to require removal. Drillers were also severely affected.
Shortly after Hurricane Rita, between Rita and Katrina, we lost a total of 5 rigs.
The Houston-based Rowan companies have been in the oil industry since the 1920s. Today, Rowan operates more than 21 mobile drilling units, or MODUs, around the world. Rowan uses a type of rig called the independent leg jackup.
We'll lower those legs, which makes the barge or the hull elevate on those legs. We then preload the rig, which means we add weight to the rig via pumping salt water on board. What that does is it settles the legs into the seabed. Once that is completed, we jack up to a drilling height, which keeps our hull out of the wave action.
After the barge is jacked up to drilling height, the weight of the entire structure now rests on huge saucer-shaped feet known as spud cans.
They're typically 26 to 30 feet tall and 40 to 60 feet diameter, very big.
At the Rowan Boneyard in Sabine Pass, Texas, the company stores leg sections and other parts of rigs that were replaced during repairs. Parts like these are held for refurbishing and reuse, or cut up for scrap and recycled. However, 4 Rowan drill rigs destroyed by the 2005 hurricanes won't be raised and brought ashore for reuse or recycling. Instead, they'll be cut up where they lie on the bottom and towed in pieces to new locations to serve as artificial reefs. It's a program regulated by the Gulf states and the federal government called Rigs to Reefs.
There were 2 general beneficiaries. One, you slow or stop coastal erosion in the areas where the reefs are placed near shore. The reefs that are in deeper water were put into place to allow for fish stock habitat development.
The program is managed by each state which has jurisdiction over the area in which the reefing site is located. Practically anything placed in the ocean acts as a magnet for sea life, and the bigger it is, the more it attracts. Yet the Rigs to Reefs program is controversial. California consistently denies new platforms as well as reefing in its waters, citing environmental concerns as well as questioning claims of benefits to marine life.
Are the platforms producing fish or aggregating fish? In California, they do both. In California, they act just like a natural reef. In the Gulf of Mexico, my understanding is that generally the platforms tend to aggregate fish, and they produce smaller numbers of fish.
Dr. Love has extensively studied underwater life around the platforms off the coast of California.
We use scuba surveys for the first 100 feet. And below 100 feet, we use a little 2-person submarine, which is about the size of a phone booth.
But Louisiana, Texas, and other Gulf states see positive results in reefing. to both coastal beaches and marine life, and carry on vigorous rigs to reefs programs. The company Rowan hired to salvage and reef its rigs is Bisso Marine. In the Gulf, companies like Bisso are kept busy removing decommissioned and damaged platforms and drilling rigs and placing them in reef sites.
Reefing is basically taking something from a location in the Gulf of Mexico where it's typically found to be damaged or destroyed, and then moving it to a location that's been approved by the federal government.
Whether salvaging or reefing, for Bisso Marine, the basic process is the same.
It really doesn't matter whether you're lifting an abandoned platform or salvaging a jackup rig or salvaging anything for that matter. It's just the act of picking it up and transporting it.
Before cutting up and salvaging the pieces of the drilling rig, all oil and other contaminants must be removed. With each piece weighing thousands of pounds, these massive structures must be carefully cabled, chained, and dismantled. For divers, a primary tool is the electric torch. Fed with compressed oxygen, divers use the torch to cut, separate, and remove the pieces section by section.
Sometimes there are pieces attached to pieces. If we did not remove those or separate those, it may become dislodged from each other and then falling apart.
Each piece of debris must be carefully rigged before the diver can begin cutting, and to facilitate transporting it to the reefing site. This part of the process is critical and differs from salvaging a land-based rig to one at sea.
There's just any number of things that can occur in a salvage operation. You know, you're taking something that's designed to be in a normal environment, and you're taking it, shaking it up, and throwing it down with great force to the seafloor in the case of a hurricane, and sort of all bets are off as far as what you find or what you think you're going to find. Sometimes there's damage and debris that you find that is just in your way. You either move it out of the way or cut it out of the way, or sometimes you just work through it.
Unlike cutting a rig up on land, which you can cut pieces off and falls on the ground, and you use crawler cranes to pick up those pieces, underwater, it's just a totally different environment. You have to rig up, you have to put chains around the pieces you're going to cut, you've got to make sure they don't fall, and if at that time while you're transporting them, you're over a pipeline or over a wellhead, you could cause damage to something else, and we're not going to do that.
Another potential hazard is the possibility of gas from the cutting torch accumulating in pockets of the debris.
Prior to making a main cut, he will drill these areas that may cause gas to accumulate. Once he starts cutting, gases will pass through confined spaces and be vented out these holes that he's drilled. If he didn't do that, what could occur is an underwater explosion. It could rupture eardrums. It's not a good place.
Today, the crew's efforts are concentrated on freeing one of the rig's legs from the mud of the seabed.
It's been difficult removing the leg sections and the spud cans. That's probably been the most difficult effort that we faced through the whole salvage operation.
The diver is cutting through the jack-up teeth on a leg. The steel is 5 inches thick. Working at depths to over 300 feet makes the diver's work even more laborious and time-consuming.
They have to continually check their cut in between burning rods to make sure they're still in the same location, and they're continuing to gain a little metal fatigue every time they burn a rod out of there.
Since Hurricanes Katrina and Rita, Bisso Marine has been constantly salvaging throughout the Gulf. It will take 5 months on this one Rowan rig to recover and reef a derrick, a drill floor, a section of hull, and 3 of the 15 legs and spud cans.
They were 140 some odd feet long, so by the time we stood it up and pulled it up out of the mud, we were lifting up about a 14-story tall building.
After the leg is pulled free, the crane will raise it from the wreck site. But the leg will remain suspended below the surface as it is being towed to the reefing site 90 miles away. After all pieces of the rig have been removed and towed away, the salvage site must be combed of debris with a device called a gorilla net,
which is a large shrimping net with wire through the braided ropes for strength, and they literally drag the site and remove all associated debris within this 1/4 mile radius.
Removing a platform and bringing it ashore is enormously expensive and can cost more than the value of the structure's refurbishing or even its recycled steel. In recognition of the savings to the owner by allowing them to reef the rig, states require a donation from the rig owner equal to half of what removing and scrapping would have cost.
The benefits to the state are obvious. They not only receive the material for the artificial reef program, they also receive funding to continue maintenance of that program. The cost to industry varies, but in general terms, you're looking at $100,000 to $200,000 for the smaller platforms, or in the case of special artificial reef sites, as much as $5 to $6 million donation to the state's particular program.
Although Gulf Coast states have embraced the Rigs to Reefs program, California hasn't. Until it does, it's likely that when Gale and other platforms are decommissioned, they'll be towed ashore and scrapped. But on the Gulf Coast, some entrepreneurs are pursuing a new alternative to scrapping and reefing, one that utilizes their robust design to harvest energy. To create new energy opportunities, a Louisiana company is taking advantage of two resources the region has more than enough of: Gulf winds and offshore boneyards. Based in New Iberia, Wind Energy Systems Technology, Inc., or WEST, is designing and creating the technology to convert idle offshore oil and gas platforms into platforms for wind turbines. By combining innovative turbine designs with existing petroleum production technology, they plan to be harvesting renewable energy from offshore wind farms in 2008. Harold Scheffler, the owner of a Cadillac dealership in Lafayette and a co-founder of West, got the idea after a conversation with a Cadillac buyer in the offshore oil business.
A customer was griping about the high cost of taking all this equipment out when they were through with it. And it was a horrendous expense. And I made the comment, if you guys knew you were in the energy business instead of the oil business, when you were through with producing oil on those platforms, you'd put wind turbines on them and have them operational for the next 100 years. And he laughed and said one of those things wouldn't produce enough power to charge a 12-volt battery on the shore.
Determined to prove his customer wrong, Scheffler sought the advice of a friend with vast experience in the industry, Herman Shellstead.
We did a basic study of that and found that the platforms were way adequate to do this.
He was elated. He was saying, wow, what a wonderful thing to do. It could take all our knowledge of 50, 60 years of putting structures out in the Gulf and apply it to a new renewable form of energy. It would keep Louisiana and all the ports and facilities in the energy business, and it would give us some hope for the future.
A recent survey by Stanford University studied 1,800 sites across the U.S. for prospective wind power generation. From this, they learned that a potential bonanza of energy existed right off the coast of Louisiana and Texas.
They ranked it from 0 to 7, with 7 being a premier site. There were only 23 Category 7 sites, and 6 of those are here in the Gulf from the mouth of the Mississippi to the Sabine River. So we sit here in a premier area in terms of wind.
Scheffler and Shellstead also went to Europe to study offshore wind farms there.
Germany has power for 22 million homes, 10% of their power. Within 5 or 6 years, we could be as much as 10% of the power if we chose to do that. We think offshore wind can play a major role in that issue. You know, it's a no-brainer. It's free, the fuel is free.
They returned satisfied that Gulf Coast offshore jackets and platforms are built much stronger than European windmill bases, far more able to withstand the stresses of both wave action and turbine vibration.
We think the technology of using a jacket that's placed on the bottom and then pilings are pushed through the legs of the jacket, that's the typical structure that's here in the Gulf, will be a much stronger platform. And we have platforms here that's been out there 50 years through many storms and hurricanes, and they're just as level as the day they were put out here.
By combining state-of-the-art wind turbine technologies with the expertise and experience that virtually wrote the book on offshore oil production, Scheffler and Shellstead see a bright future for offshore wind farms. There are over 4,000 platforms in the Gulf of Mexico. Scheffler and Shellstead estimate that approximately 1,000 of them can be used for wind farms. Though they first attempted to build in state waters off Louisiana, their first wind farm will be off Galveston, Texas.
Texas has the infrastructure to sell the power, to receive it into the grid, to allow for renewable energy credits.
Before placing their wind turbines, they must first complete research on wind patterns and routes of migratory birds. This study is underway with the aid of a meteorological tower they've erected on a platform on the Galveston site. If the study concludes the site is appropriate, a new topside will be installed to support the first of their wind turbines.
We also have a new design that is a marriage between the wind industry and the oil industry. Our new designs have three major features, one of which is a vibration isolator to take the vibration out of the platform. The next is a retractable leg where the actual center member is retracted down to the water level. And third, we have folding blades so we can prepare our wind farm to withstand a direct hit from a hurricane.
If we go with 2.5 megawatt units or 3 megawatt units, which we're leaning towards, propeller size will be 155 feet. 310 feet is the diameter of the whole unit. The hub height is 280 feet.
The power from the individual platforms will be sent to a platform that serves as a gathering station, which would regulate the power and send it to shore through an armored underground cable. The work of converting the platforms will be done at local fabrication facilities, providing jobs and bolstering the local economy, transforming offshore boneyards built for pumping oil into wind energy generators.
We'll go to the scrap yard and take the steel platforms that are coming from offshore. We may get a platform that's out there in 600 feet of water. And out of that one platform, we could make many platforms to go in this water that's 10 feet, just by cutting it and redesigning the top and turn them to a viable platform for offshore wind.
Herman and Harold continue to explore ways to establish wind farms in Louisiana's waters. One of the sites they're most interested in is the Rabbit Island field.
What we're looking at is concrete platforms which are no longer built. They were generally in very shallow water, generally in state waters. One of the major power companies in Louisiana is looking at putting a system here.
Unlike steel, concrete platforms cannot be taken ashore to be scrapped and recycled. If a wind farm is developed here, it would convert an abandoned concrete boneyard into yet another energy source for the state of Louisiana. In recent years, as idle offshore oil and gas platforms are decommissioned and removed, there has been a unique variety of proposals for alternate uses, some of which have already become reality. The same boneyards where platforms and drilling rigs are being refurbished or scrapped are hard at work converting them to offshore laboratories, radar stations, and diving resorts, even as a base station for an elevator to the stars. It may sound like science fiction, but according to a growing number of scientists and engineers, converted oil platforms could be deployed as a critical component in a new space program unlike any other previously attempted. In this technology, payloads and people would be transported to Earth orbit and beyond by riding an elevator to an orbiting satellite along a tether attached to an Earth station on a converted offshore platform.
The space elevator, in simplest terms, has a ribbon with one end attached to Earth, the other end up in space, and it can be ascended by mechanical climbers. It's access to space without rockets.
The end of the ribbon attached to the Earth would be anchored to a converted oil platform. With a deck tied to steel pilings driven deep into the seabed, this versatile design would serve as the base station for operating the space elevator. Space travel experts, including NASA scientists, assure us that the dynamics are simple, straightforward, and could work.
To deploy the space elevator, you launch a satellite up into orbit, it deploys down a ribbon, you grab that ribbon at Earth, and we send climbers up that ribbon to make it larger, and that builds up the full space elevator.
Gravity would pull the ribbon connecting the space station and the former oil platform straight, in much the same way that a string attached to a ball would stay straight if you swung it around.
The ribbon is 62,000 miles long, and the only reason it keeps it from breaking is that we're going to be using the strongest material that's ever been made. It's called carbon nanotubes. It's a tubular shape arrangement of carbon, very similar to graphite, and it's pound for pound several hundred times stronger than steel, and it's much stronger than anything else that's ever been made.
The mechanical climbers, or elevator cars, would be powered by electricity beamed up from the Earth station by laser. The energy efficiency of using these mechanical means to travel to space, as opposed to rocket power, could make the space shuttle a thing of the past.
Today, the shuttle can launch about 20 tons into space, about the same as a large truck. The space elevator, the first one, the small one, we can launch about 13 tons, and that can go 22,000 miles up, or it can take it further and launch it off the end to Moon or Mars. So we're talking about a system that can take a lot more cargo, and the elevator can be expanded to 20 tons, 50 tons, 100 tons, and take it up on a daily basis.
All program confirmed.
Though NASA remains committed to using rockets to escape Earth's gravity, they are encouraging development of the space elevator with ongoing Centennial Challenge contests.
There are two competitions. One is a climber challenge, where you build a climber, it has to use beamed power, no connections, and it has to ascend a ribbon in 2007, 100 meters, 300 feet, straight up, and it has to do that in roughly 1 minute. The one who does it fastest with the most payload wins. The other challenge is a tether challenge, and that's to develop the high-strength materials required for the ribbon. It's a high-tech tug of war. You have two tethers, small ones, they pull against each other. Whichever one breaks first is the loser. The NASA Centennial Challenge Office is supplying the prizes of, right now, $500,000 for each of the two events, and it could go up as high as $2 million over the next couple of years.
Though many proposals for reusing oil platforms can rely on proven technology, economics are still significant.
It costs about $400,000 a year to maintain a platform above the waterline before you can even start talking about making money. So all of these ideas may be great, but the economics may just not be there.
There is, however, another frontier for offshore platforms that only boneyard technology can address: salvaging and removing platforms from deep-sea environments.
You get out into 600-700 feet of water, it's certainly possible, but you are limited strictly to saturation diving, which in those depths of water are very lengthy operations and very demanding on the divers and very expensive operations.
With oil and gas companies pushing the envelope to depths of 10,000 feet and beyond, future salvage operations will face greater challenges than ever. But with the industry's record of achievement, it seems likely that these problems will be resolved in the same way the offshore pioneers first ventured from land to the sea, by putting cutting-edge technology in the hands of a can-do culture's native ingenuity, and a little help from the boneyard.